Raft Demystified, Building Reliable Distributed Systems. 1. The Unreliable World. Why we need distributed systems and consensus. Imagine trying to keep track of every single transaction in a bustling global marketplace, with transactions happening across continents every millisecond. Or picture managing the ever-changing state of millions of online users, ensuring they can seamlessly connect, share, and consume content, no matter where they are or which device they're using. These aren't just hypotheticals. They are the daily challenges faced by companies running the digital services we rely on. And they are the very reason we build distributed systems. A distributed system, at its core, is a collection of independent computers that appears to its users as a single, coherent system. Instead of housing all data and processing power within one monolithic machine, work is spread across many. This approach isn't a mere technological preference. It's a fundamental necessity for modern applications. Why do we embrace this complexity? The allure lies in the powerful benefits. Scalability. A single computer has finite resources. To handle a growing number of users or data, you can simply add more machines to the distributed system. This horizontal scaling is often far more cost-effective and flexible than upgrading a single, monstrously powerful machine. Fault tolerance. If one machine in a distributed system fails, the others can pick up its slack. This resilience makes applications more robust and less prone to costly downtime. Imagine a website crashing because its sole server failed. Distributed systems aim to prevent this single point of failure. Performance. Spreading the workload can lead to faster processing, especially for complex operations that can be broken down into smaller, parallelizable tasks. Data can also be placed closer to users, reducing network latency. Geographic distribution. Users are global, and so are their data needs. Distributed systems can span multiple data centers, ensuring low latency for users worldwide and providing disaster recovery capabilities should an entire region go offline. Despite these compelling advantages, distributed systems are inherently more challenging to build and manage than their single-machine counterparts. This is where the world becomes unreliable. In a distributed environment, you contend with network delays, messages that get lost or reordered, machines crashing unexpectedly, clocks that aren't perfectly synchronized, and the general difficulty of coordinating independent components. It's like orchestrating a global symphony where individual musicians might arrive late, forget their sheet music, or have their instruments suddenly go silent, yet the show must go on, perfectly in tune. The problem of coordination, when everyone needs to agree. The complexity of distributed systems truly surfaces when these independent machines need to agree on a shared piece of information, or state. Consider a simple online banking transaction. When a user transfers $100 from account A to account B, two fundamental things must happen. Account A must decrease by $100, and account B must increase by $100. In a single machine system, this is straightforward. A database transaction ensures both updates happen together, or neither does. But what if account A is managed by server X and account B by server Y, located in different data centers? Server X processes the debit, server Y processes the credit. What happens if server Y crashes before receiving the credit instruction, or if the network link between them fails? What if both servers think they successfully completed the transaction, but in reality, one failed and the other didn't know? This highlights the critical challenge of data consistency. In a distributed system, how do we ensure that all participants see the same, most up-to-date, and correct view of shared data, especially in the face of inevitable failures? Do we prioritize seeing the absolute latest data, even if it means waiting for the system to synchronize? Or do we prioritize quick access to some data, even if it might be slightly out of date? These trade-offs are often captured by concepts like eventual consistency versus strong consistency. While eventual consistency is suitable for some applications, like social media feeds where a minute's delay isn't critical, many core business functions, such as financial transactions or inventory management, demand strong consistency. Everyone must agree on the identical, most recent state of the system all the time. The cost of disagreement, from theory to outage. when distributed systems fail to coordinate and achieve consistency. The consequences can range from minor discrepancies to catastrophic failures. Split brain scenarios. Perhaps the most notorious failure mode is split brain. This occurs when a single distributed system, due to a network partition, believes it has two or more independent, fully functional brains or leaders. Each brain might then make decisions or perform updates independently, leading to data divergence and severe inconsistencies. Imagine our banking system, but now account A is managed by two servers, both believing they are the primary. If a $100 debit comes to one and a $50 debit to the other, the account state becomes undefinable. Which is the truth? Data corruption and loss. Without consensus on the order of operations, data can become corrupted, lost, or overwritten incorrectly. If two transactions modify the same record and the system can't agree on the correct order, the final state will be indeterminate. Service unavailability. If components cannot agree on a leader or a consistent state, they might simply stop processing requests, leading to application outages. Or they might process requests incorrectly, which can be even worse than an outage, as it results in silent data errors or incorrect system behavior. Consider an e-commerce platform that needs to update inventory counts across multiple warehouses. If a customer buys the last item of a product, the system must atomically decrement the inventory. Without careful coordination, it's possible for two customers to successfully buy the same last item, leading to an oversell and a very unhappy customer. Or, even worse, the inventory might display one quantity on the website, while the warehouse system shows another, creating chaos for fulfillment. These scenarios illustrate a fundamental truth. In a distributed world, agreeing on a shared sequence of events or a single value is paramount. This is precisely the problem that consensus algorithms are designed to solve. Introducing consensus, the foundation of reliability. A consensus algorithm allows a group of independent processes, the computers in our distributed system, to agree on a single, shared value or decision, even if some of those processes fail or messages are lost. It's the digital equivalent of voting on a crucial decision in a committee, where every member's vote counts. And even if some members are absent or communication is spotty, a definitive outcome must be reached and agreed upon by the majority. The goal of a consensus algorithm isn't just to reach agreement, but to do so safely and reliably. This means ensuring properties like agreement, all non-faulty processes eventually agree on the same value. Validity. The agreed-upon value was proposed by at least one process. Termination. All non-faulty processes eventually reach a decision. Integrity. A process agrees on at most one value. These algorithms are the bedrock upon which many high-availability and strongly consistent distributed systems are built. They allow systems composed of many unreliable parts to collectively behave as one highly reliable whole. They enable critical functions like leader election, determining which node in a cluster is the primary, responsible for coordinating activities. Configuration management, ensuring all nodes agree on the system's current settings. Distributed locking, allowing only one process at a time to access a shared resource. Replicated log, maintaining a consistent, ordered sequence of operations across all machines. The problem of achieving consensus is surprisingly complex. Researchers have grappled with its intricacies for decades, leading to a rich history of theoretical advancements and practical implementations. For a long time, one algorithm, Paxos, stood as the academic gold standard. But while supremely correct, it was often described as difficult to understand and implement. This paved the way for a new approach, specifically designed to be comprehensible yet equally robust, an algorithm called Raft. We'll delve into its fascinating origins and design goals in the next chapter. 2 Before Raft. A brief history of consensus. The concept of distributed consensus isn't new. It's a problem that has plagued computer scientists and engineers since the early days of networked computing. From the initial glimmerings of sharing resources to the massive cloud infrastructures of today, the fundamental challenge has remained. How do independent machines agree on a common truth, especially when failures are inevitable? Early attempts and challenges. early distributed systems quickly bumped into this wall. Imagine a group of military generals, separated by enemy territory, needing to agree on a battle plan and the exact time to attack. Some generals might be traitors, or messengers might be captured, or communication lines might be cut. This famous analogy, known as the Byzantine general's problem, beautifully illustrates the core difficulties. How do you achieve consensus in the presence of unreliable communication and potentially malicious or faulty participants? While Raft doesn't specifically address Byzantine faults, it assumes fail-stop behavior where nodes either work correctly or simply stop responding. The underlying challenge of agreeing despite partial failures is universal. Even without malicious actors, simply agreeing on a value among several machines proved incredibly hard. Systems had to contend with the famous FLP impossibility theorem, named after Fisher, Lynch, and Patterson. This theorem, proven in 1985, states that in an asynchronous distributed system, where there are no guarantees on message delivery times, where even a single process can crash, it is impossible to guarantee that all non-faulty processes will eventually agree on a single value. This theorem wasn't a death knell for distributed systems, but rather a profound insight. It meant that real-world consensus algorithms must make compromises. They might relax the asynchronous assumption, e.g., by using timeouts, or they might make probabilistic guarantees, or they might simply assume that outright crashes are the only failure mode. Understanding this theoretical limit helps appreciate the ingenuity behind practical consensus algorithms. Paxos, the gold standard, and its reputation. For many years, the undisputed intellectual leader in the field of distributed consensus was an algorithm designed by Leslie Lamport, first published in 1990 and later refined. This algorithm is called Paxos. Lamport, a brilliant computer scientist and Turing Award winner, framed Paxos using an analogy of a democratic parliament on a fictional Greek island. In this parliament, various members, acceptors, proposers, learners, attempt to reach consensus on a decree, a value. The algorithm works in two phases. Prepare phase. A proposer, a potential leader, tries to reserve the right to propose a value by asking acceptors, the nodes responsible for remembering proposals, if they've already promised to accept a higher-numbered proposal from someone else. Accept phase. If the proposer gets promises from a majority of acceptors, it then proposes a specific value. If an acceptor hasn't promised to a higher-numbered proposal, it accepts the value. Once a majority of acceptors accept a value, it's considered chosen. Paxos is renowned for its correctness. It rigorously guarantees safety properties. Once a value is chosen, it remains chosen, and all learners eventually agree on the same value. No matter what combination of failures occur, Paxos ensures that the system doesn't diverge. However, Paxos also developed a formidable reputation for complexity. Lamport himself acknowledged this, humorously writing that the formal paper was found difficult to understand. The original description was concise but highly abstract, and common implementations often involved extensions, like multi-Paxos, to make it practical for continuously selecting sequences of values, like a replicated log. Practitioners found it hard to translate the theoretical elegance into concrete, bug-free implementations. Many smart engineers understood Paxos, but few felt truly comfortable implementing it. This created a significant gap between the academic theory and the practical needs of building robust distributed systems. The motivation for Raft. By the early 2010s, the landscape of distributed systems was exploding. Technologies like Hadoop, Cassandra, and eventually cloud platforms were becoming commonplace. Teams needed to build highly available, fault-tolerant services, and distributed consensus was a key ingredient. Yet, while Paxos was correct, it wasn't solving the practical problem of ease of implementation and understandability. Debugging a Paxos implementation was notoriously difficult, akin to untangling a complex knot. This led Diego Ongaro and John Ousterhout, then at Stanford University, to embark on a quest. Their goal wasn't to invent a more powerful consensus algorithm, but a more understandable one. They set out to find an algorithm that was simpler to reason about, easier to teach, and consequently, more straightforward to implement correctly. They called their brainchild Raft. The authors conducted an experiment to validate Raft's understandability. They taught both Paxos and Raft to students and then tested their comprehension. The results were striking. Students consistently performed significantly better on questions related to Raft. This provided empirical proof that Raft indeed delivered on its core promise of understandability. Raft's design goals. Raft's design explicitly focused on overcoming the understandability barrier of Paxos while still retaining all the necessary safety and liveness properties. The key design goals that guided its creation were strong leader. Unlike Paxos, where the concept of a definitive leader can be somewhat fluid, multiple proposers can be active, Raft firmly places the burden of coordination on a single, elected leader. Most decisions go through the leader, simplifying the logic. This leader-centric approach is one of Raft's most prominent features, contributing to its understandability. Understandability through decomposition. Raft breaks down the consensus problem into 3 relatively independent subproblems, which are tackled separately. Leader election, how a new leader is chosen when the current one fails. Log replication, how the leader consistently replicates log entries to followers and ensures they remain synchronized. Safety, how to guarantee that all important safety properties are met. An entry committed on one machine will eventually be committed on all machines and never change. Strong consistency. Raft ensures that once a log entry has been committed, it will never be reverted or changed. This is crucial for applications requiring strict data integrity. Safety guarantees. Raft provides strong safety guarantees, meaning that even in the face of network partitions, crashes, and message loss, it will never return an incorrect result or lose committed data. It achieves this primarily through its strict rules around leader election and log matching. Performance. While understandability was the primary driver, Raft is also designed to be efficient in common cases, performing well under normal operating conditions. Membership changes. Raft supports dynamic cluster membership changes without losing consistency, meaning you can add or remove nodes from a running cluster safely. This is a critical feature for practical, evolving distributed systems. By prioritizing these goals, especially understandability, Raft emerged as a highly practical and widely adopted algorithm. It's the engine behind many of today's staple distributed systems, from configuration services to distributed databases. In the next chapter, we'll begin to dismantle Raft piece by piece, starting with its fundamental building blocks. Server states, terms, and how a leader is elected. 3 Raft's foundation, states, terms, and roles. To truly grasp Raft, we must first understand its fundamental building blocks. The 3 distinct states a server can be in, the concept of terms as Raft's logical clock, and the crucial process of leader election that brings a distributed system to order. The core idea. Leadership centricity, one of Raft's most powerful simplifications, and a key differentiator from Paxos, is its strong leader approach. In Raft, consensus is achieved by electing a single, authoritative leader responsible for managing the replicated log and coordinating all client interaction. All client requests that modify the system's state must go through the leader. This centralization significantly simplifies the logic of log replication and commitment, making the algorithm much easier to reason about. It's like having a single conductor for an orchestra, rather than everyone trying to play their own tune simultaneously. Server states and their transitions. Every server in a Raft cluster operates in one of 3 mutually exclusive states. Follower, this is the default state for a server when it starts up or when it recognizes a valid leader. Followers are passive, they don't issue requests. Instead, they respond to request vote RPCS, remote procedure calls from candidates and append entries RPCS, which serve as both heartbeats and log replication messages from the leader. If a follower doesn't hear from the leader or a candidate for a certain period, it can become a candidate itself. Candidate, when a follower believes the leader has failed or the cluster needs a new leader, e.g., during startup, it transitions to the candidate state. In this state, a server actively seeks to become the new leader. It increments its current term, votes for itself, and sends request vote RPCs to all other servers in the cluster, asking for their vote. If a candidate receives votes from a majority of servers, it then transitions to the leader state. Leader. There is only one leader in a Raft cluster at any given time. The leader is responsible for handling all client requests. It appends new log entries to its own local log, replicates them to all followers, and tells them when it's safe to commit those entries. The leader also sends periodic append entries, heartbeat, RPCs to all followers to maintain its authority and prevent followers from timing out and starting new elections. These states are not static. Servers constantly transition between them based on events like timeouts, receiving RPCs, or gaining a majority of votes. The flow usually goes follower candidate leader or follower candidate follower if another server wins the election or the current leader reappears. A leader can also revert to being a follower if it discovers a new leader with a higher term. Terms. Raft's logical clock. Raft uses terms as its logical clock, a fundamental concept for ensuring safety and preventing stale information from causing inconsistencies. A term is a single, monotonically increasing integer. It functions like an epoch number or an election period. Every time a leader election occurs, a new term begins and its term number is incremented. Each server stores its current term number. This term number is included in every request vote and append entries RPC. When a server receives an RPC with a higher term number than its own, it immediately updates its current term to the higher value and reverts to a follower state. This is crucial. It ensures that servers always defer to the most up-to-date information about the cluster's leadership. If a request contains a stale term number lower than the server's current term, the request is rejected. This prevents old leaders or candidates from disrupting the cluster. Terms ensure that once a leader is established for a given term, only that leader or a new leader from a higher term can make progress. Discarding messages with old terms or updating to a new term correctly is vital for Raft's safety properties. The dance of election. The process of leader election is perhaps the most dynamic and critical part of Raft's operation. It's how order is established in a potentially chaotic distributed environment. Election timeout. Every follower maintains an election timeout. This is a random period, typically between 150 ms and 300 ms, during which the follower expects to receive heartbeats from the leader. The randomness is key. It helps prevent all followers from timing out simultaneously and initiating an election, which could lead to split votes, where no candidate can achieve a clear majority. If the follower doesn't hear from the leader within this timeout, it assumes the leader has failed or communication has been lost, and it's time for a new election. Becoming a candidate. Upon election timeout, the follower transitions to the candidate state. It performs 3 crucial actions. It increments its current term. This signifies the start of a new election period. It votes for itself. It resets its election timer, indicating it has just started an election and will wait for responses. Request vote RPCs. The candidate then sends request vote RPCs to all other servers in the cluster. These messages contain the candidate's new term, the candidate's ID, the index of the candidate's last log entry, the term of the candidate's last log entry. These last 2 pieces of information are used for a safety check, which we'll discuss in Chapter 5. A server will only vote for a candidate if the candidate's log is at least as up-to-date as its own. Winning the election. A candidate wins the election and becomes the new leader if it receives votes from a majority of the servers in the cluster, including its own self-vote. This majority rule, also known as a quorum, is fundamental to Raft's correctness. It ensures that only one leader can be elected per term and that any committed data will have been seen by a majority of servers. Once a candidate wins, it immediately begins sending append entries heartbeats to all other servers to establish itself as the new leader and prevent other servers from starting new elections. Stepping down. A server in the candidate or leader state can revert to a follower state if it discovers that another server has a higher term. For instance, if a candidate sends a request vote RPC and receives a response from another server indicating a higher term, the candidate immediately steps down and becomes a follower. Similarly, if a leader receives an append entries or request vote RPC from another server with a higher term, It recognizes that a newer leader has emerged or is attempting to emerge, and it gracefully steps down, becoming a follower. This behavior ensures that the server with the highest term always dictates the cluster's state. Illustrative example: a simple election in a 3-server cluster. Let's imagine a cluster with 3 servers, S1, S2, and S3. S1 is currently the leader. Initial state: S1 leader term 5, S2 follower term 5, S3 follower term 5. Leader failure: S1 crashes or becomes isolated from S2 and S3. Timeout: S2 and S3, not receiving heartbeats from S1, will eventually time out. Because of the randomized election timeouts, let's say S2 times out first. S2 becomes candidate. S2 increments its term to 6, votes for itself, and transitions to candidate state. It sends request vote RPCS to S1 and S3. S3 votes for S2. S3 receives S2's request vote RPC. Since S2's term, 6, is higher than S3's current term, 5, S3 updates its term to 6 and grants its vote to S2, assuming S2's log is up to date, which we'll cover later. S3 then resets its election timer. S1 is down, S1 doesn't respond. S2 wins, S2 receives votes from itself and S3. This forms a majority, 2 out of 3. S2 becomes the new leader for term 6. New leader heartbeats. S2 immediately starts sending append entries heartbeats to S1 and S3. S3 becomes follower. S3 receives append entries from S2, leader, term 6. It's already in term 6 and recognizes S2 as the legitimate leader, so it remains a follower. 10. S1 recovers. If S1 eventually recovers and reconnects, it will receive an append entries heartbeat from S2, which has a higher term, 6, than S1's last known term, 5. S1 will update its term to 6 and revert to being a follower, recognizing S2 as the current leader. Addressing election edge cases. While the basic election process is straightforward, Raft accounts for edge cases to ensure robust behavior. Split votes. If multiple followers time out around the same time and become candidates, it's possible none of them receive a majority of votes. For example, in a 5-server cluster, if 2 servers vote for candidate A and 2 for candidate B, and 1 for itself, no one wins the election. Raft handles this gracefully. No leader is elected for the current term. Each candidate times out again with a new randomized timer, increments its term, and starts a new election. The randomized timers make it highly probable that one candidate will time out earlier in the next round, giving them a head start and increasing their chances of winning. Network partitions. If a cluster is split by a network partition, e.g., 3 servers versus 2 servers, each partition might attempt to elect its own leader. However, Raft's majority rule prevents 2 leaders from being elected in the same term. Only the partition that can muster a majority of the total servers will successfully elect a leader and make progress. The minority partition will be unable to elect a leader and will simply remain in a non-leader state until the partition heals. This is a critical safety property. While the system might become partially unavailable, it will never enter a state of conflicting leaders or diverging data. The meticulous design of Raft's selection process, with its reliance on terms, randomized timeouts, and majority rule, lays the groundwork for ensuring that a single, consistent leader can always be established, even in the tumultuous world of distributed systems. With a leader in place, the cluster can then move on to its primary function, replicating client commands. This brings us to the very heart of Raft, log replication. For the heart of Raft, log replication. With a leader firmly established, the Raft cluster can now fulfill its primary purpose: accepting client requests and ensuring they are consistently and durably applied across all servers. This crucial function is handled by Raft's log replication mechanism, which is designed for clarity and robustness. The immutable log, central to Raft's operation. At the core of Raft's operations is the replicated log. Think of this log as a sequential, append-only record of every command or operation that modifies the system's state. It's an ordered sequence of entries, where each entry represents a single command proposed by the client. Each entry in the log contains 3 key pieces of information: index, a unique, monotonically increasing number indicating the entry's position in the log. This is crucial for ordering. Term: the term number when the entry was introduced by the leader. This links the log entry to the specific leadership period in which it was created. Command: the actual operation to be executed by the system's state machine. The log is immutable once an entry is at a given index and term. This means an entry at a certain index and term cannot be changed once it's written. Raft achieves consistency by ensuring that all logs eventually become identical, containing the same sequence of committed entries. Imagine the log as a bank ledger, where each entry is a transaction record. For the bank's accounts to be consistent, every branch, server, must have an identical, ordered list of all historical transactions, commands, and state machines. Before we dive into how logs are replicated, it's important to understand what those commands in the log entries actually do. Client requests, such as set key X to value Y, increment counter Z, or transfer money from A to B, are transformed into these commands. When a Raft server applies a committed log entry, it executes the command contained within that entry against its state machine. A state machine is simply the application logic that takes in commands and updates its state accordingly. For instance, if the command is set key X to value Y, the state machine updates its internal key value store. If the command is transfer money, the state machine updates the account balances. For Raft to work correctly, all servers must start with the same initial state and apply the same sequence of committed commands in the same order. If they do, they will all end up in the same final state, regardless of failures or messages delays. This is the essence of building a fault-tolerant, strongly consistent system on top of Raft. Replicating log entries, the append entries RPC. The leader is solely responsible for accepting client requests and replicating them to followers. It does this primarily through the append entries RPC. This RPC is the workhorse of Raft. It serves a dual purpose: heartbeats. If the leader has no new log entries to send, it still periodically sends empty append entries. These heartbeats are crucial for followers to know the leader is still alive and maintaining its authority, preventing election timeouts. Log replication. When a client sends a command to the leader first appends the command as a new entry to its own log. Then, it sends append entries RPCs to all followers, telling them to append this new entry and any preceding uncommitted entries to their logs. An append entries RPC contains several important parameters. Term: the leader's current term, used to detect stale leaders. Leaderid, so followers know who the current leader is. Prevlog index, the index of the log entry immediately preceding the new entries being sent. Prevlog term, the term of the log entry at Prevlog index. Entries, an array of new log entries to be stored on the follower empty for heartbeats. Leader commit, the index of the highest log entry known to be committed on the leader, used by followers to update their committed index. When a follower receives an append entries RPC, it performs several checks to ensure consistency. Term check. If the leader's term is less than the follower's current term, the follower rejects the RPC and tells the leader its higher term. The leader, if it's truly stale, will then step down. Consistency check log matching. This is perhaps the most critical part of append entries. The follower checks if an entry at Prevlog index exactly matches the Prevlog term in its own log. If there's no entry at Prevlog index in the follower's log, or if the term at Prevlog index doesn't match Prevlog term, then the follower's log is inconsistent with the leader's. The follower rejects the append entries RPC and returns a failure. If the check passes, it means the follower's log is consistent with the leader's up to that point. The follower then appends any new entries received in entries to its log. If the follower's log already contains an entry at a given index, but with a different term than the leader's, it means the follower has a conflicting entry. In this case, the follower deletes that conflicting entry and all subsequent entries, then proceeds to append the leader's entries. Upon receiving a response to its append entries RPC, the leader updates its internal state for that follower, specifically tracking the next index. The next log entry index, the leader needs to send to that follower and match index, the highest log entry index known to be replicated on that follower. Illustrative example: leader replicates log entries. Imagine a cluster of 3 servers: L leader, F1 follower, F2 follower. Client request. A client sends a command set x equals 10 to the leader L. Leader appends. Leader L appends index 5, term 3, set x equals 10 to its local log. Let's say its leader commit is currently 4. Leader sends append entries. L sends append entries RPCs to F1 and F2. RPC includes term equals 3, leader ID equals L, prev log index equals 4, prev log term equals 3, entries equals index 5, term 3, set x equals 10, leader commit equals 4. Followers accept. F1 and F2 receive the RPC. They both check their logs at index 4 and confirm the term is 3. They then append the new entry index 5, term 3, set x equals 10 to their own logs. Followers respond. F1 and F2 respond to L, indicating success. Leader updates. L receives successful responses from F1 and F2. Now index 5 has been replicated to a majority, L, F1, F2. Commitment to the state machine. When truth is achieved, a log entry is not considered truly durable and truthful until it has been committed. Only committed entries are applied to the state machine. The rules for committing an entry are crucial for Raft's safety. Majority replication. A log entry is committed if it has been replicated to a majority of servers in the cluster. This is checked by the leader. The leader calculates the highest index for which it has received successful append entries responses from a majority of its followers. Current term restriction. This is a subtle but vital rule. A log entry can only be committed if it was created by the current leader, i.e., its term matches the leader's current term, and it has been replicated to a majority of servers. Entries from previous terms cannot be committed directly by simply being replicated to a majority. They are implicitly committed when a later entry from the current term is committed. This rule prevents scenarios where a new leader commits an old, partially replicated entry that would otherwise be overwritten by a newer leader with a different sequence of entries. We will explore this critical safety property more deeply in Chapter 5. Application. Once an entry is committed by the leader applies it to its local state machine. In subsequent heartbeats or append entries RPCs, the leader will tell followers about the newly committed index via leader commit. Followers, upon receiving this, will then also apply all committed entries up to leader commit to their own state machines, always applying them in log order. This careful choreography between leader and followers, driven by the append entries RPC and guided by strict commitment rules, ensures that the replicated log remains consistent across the cluster. Every server ends up with an identical, ordered sequence of committed commands, leading to identical state machines. This brings us to Raft's ironclad guarantees, which are the subject of our next chapter. 5. Raft's ironclad guarantees. Safety and consistency rules. Raft prioritizes safety above all else. While achieving understandability was its primary design goal, this never compromises its ability to guarantee strong consistency even in the face of network outages and server crashes. These guarantees are enforced by a set of strict rules that govern leader election and log replication. Understanding these rules is key to appreciating Raft's robustness. Raft's core safety properties. The designers of Raft distilled its safety guarantees into 2 main properties, which are then enforced by specific rules. Election restriction. Property. In any given term, at most one leader can be elected. More importantly, a candidate cannot win an election unless its log contains all committed entries from previous terms. Purpose. This rule ensures that a newly elected leader always possesses the most complete and up-to-date log among the majority of servers. It prevents an older, stale server from becoming a leader and then overwriting or losing previously committed data. How it's enforced. When a follower receives a request vote RPC from a candidate, it only grants its vote if the candidate's log is at least as up-to-date as its own. Up-to-date is defined as follows. If the candidate's last log term of its last log entry, is greater than the follower's last log term, the candidate is more up-to-date. If the last log terms are the same, then the candidate with the larger last log index, meaning a longer log, is considered more up-to-date. This means that if a majority votes for a candidate, that candidate's log must contain all committed entries. Why? Because for an entry to be committed, it must be present on a majority of servers. If a candidate now receives votes from a majority, at least one server in that majority must have had the committed entry. And if the candidate is more up-to-date than that server, it must also have the committed entry. Log matching property. Property. If two logs contain an entry with the same index and term, then they are identical in all preceding entries. Furthermore, if two logs contain an entry with the same index and term, then the logs are identical from that entry's index forward. Purpose. This property simplifies reasoning about log consistency. It means you only need to compare the very last entry of two logs to understand their relationship. It ensures that once logs converge at a certain point, they don't diverge later. How it's enforced. The append entries RPC plays a critical role here. When a leader sends append entries messages, it includes the prevlog index and prevlog term, the index and term of the log entry immediately preceding the new entries being sent. When a follower receives this RPC, it must verify that its own log actually contains a matching entry at that prevlog index with that prevlog term. If there's a mismatch, the follower rejects the append entries request and tells the leader to try an earlier prevlog index. The leader then decrements its next index for that specific follower and retries the append entries RPC with an earlier, more common prefix. This iterative backtracking continues until the leader finds the latest log entry where its log and the follower's log match. Once a match is found, any conflicting, or simply missing, entries in the follower's log from that point onward are truncated and overwritten by the leader's consistent entries. This efficient mechanism guarantees that once logs align at a particular entry, they remain identical from that point forward. Commit rule deep dive. Why the current term rule matters. While a log entry is considered committed if it's replicated to a majority of servers, Raft has a crucial nuance that differentiates it from simpler replication strategies and strengthens its safety. A leader can only commit log entries with its own current term entry. It cannot commit entries from previous terms just by getting them replicated to a majority. Why is this rule necessary? Consider this complex scenario. S1 is leader term 2. S1 creates and replicates log entry IX3 t equals 2 to S2. S3 is down, S1 crashes. IX3 t equals 2 is replicated to a majority 2 out of 3, but not yet committed. S5 is elected leader term 3. After S1 crashes, S3 recovers, and S5, another server, gets elected as leader for term 3. S5's log is old, but S5 wins the election by getting votes from S2, which has IX3 t equals 2, and S3, which might not. Crucially, S5 must have IX3 t equals 2 in its log or be more up-to-date by the election restriction. S5 then replicates a different log entry, IX3 t equals 3, to S2 and S3, overwriting S2's IX3 t equals 2. S5 crashes. S1 recovers and is elected leader term 4. S1, which still has IX3 t equals 2, manages to get elected as leader in term 4. This is possible if S1, with IX3 t equals 2, gets votes from servers that didn't experience the term 3 leader S5 and still have IX3 t equals 2. S1 now sees that IX3 t equals 2 is replicated on a majority of nodes itself, and maybe one of the others that didn't get overwritten by S5, so it wants to commit it. If S1 could commit IX3 t equals 2, in term 4 just because it's on a majority, we would have a huge problem. The IX3 t equals 2 entry would be committed, but IX3 t equals 3 from S5, a different entry at the same index but higher term, would also have possibly existed for a brief time and could have been committed by S5 if it had been alive long enough to replicate one of its own current term commands. Raft prevents this type of invalid commitment. Raft's safeguard. A leader only commits an entry if it came from its current term and is replicated to a majority. If a leader sees that an entry from a previous term is replicated on a majority, it only commits that prior term entry if and when a new log entry from the current term, i.e., created by the current leader, is successfully replicated to a majority and thus committed itself. This piggybacking ensures that all preceding entries are validated by the current leader. It means that IDX3 t equals 2 in our scenario above would not be committed by a term 4 leader until the term 4 leader successfully replicates and commits one of its own term 4 entries. This sequence ensures agreement, leader stickiness, minimizing unnecessary disruptions. While Raft embraces the inevitability of new elections, it also aims to keep an elected leader stable for as long as possible. Frequent leader changes, known as leader flapping or fencing, can degrade performance and availability. Raft promotes leader stickiness through randomized election timers. As discussed, this prevents simultaneous elections and helps consolidate votes for a single candidate. Heartbeats. The leader's constant append entries, heartbeats reset followers' election timers, preventing them from initiating new elections. Reverting to follower on higher term. A leader will immediately step down if it encounters a higher term. This ensures that a stable, true leader for the highest term takes precedence, rather than having concurrent leaders struggling for control. Handling network partitions and crashes. Raft is designed to maintain safety even when parts of the system fail. Network partitions. If a network partition occurs, e.g., the cluster splits into two smaller groups, only the partition that contains a majority of the servers can elect a leader and continue making progress. The minority partition will be unable to form a quorum and thus cannot elect a new leader or commit new log entries. This means that while a minority group might become temporarily unavailable, it can never generate conflicting, incorrect state, or commit new, divergent data. Once the partition heals, the servers in the minority partition will discover the leader in the majority partition, which will have a higher term, and update their logs accordingly. Server crashes. Raft handles server crashes transparently. If a follower crashes, the leader simply continues replicating to the remaining healthy followers. When the crashed follower recovers, it contacts the leader, finds its log is behind, and the leader updates it using append entries RPCS, bringing it up to speed. If the leader crashes, an election is triggered and a new leader is elected. The new leader then takes over, ensuring the system can continue processing requests. The quorum. The concept of a majority, or quorum, is central to all these safety guarantees. A Raft cluster with n servers needs n/2 plus 1 servers to form a quorum. This means a 3-server cluster needs 2 servers for a quorum, a 5-server cluster needs 3, and so on. The quorum ensures that any committed log entry must be present on at least 1 server in any subsequent majority. This overlap guarantees that once an entry is committed, it effectively becomes irreversible and universally true. By meticulously enforcing these safety rules, Raft ensures that data remains consistent and operations are performed reliably, even in the unpredictable and failure-prone world of distributed systems. This strong foundation allows Raft to manage not just fixed clusters, but also dynamic ones, which is the subject of our next chapter. 6 dynamic clusters. Membership changes and reconfigurations. A production distributed system is rarely static. Components fail, hardware needs to be upgraded, capacity must be scaled up or down, and server locations may shift. This means that the set of servers participating in a Raft cluster, its membership or configuration, must be able to change dynamically without violating the algorithm's safety and consistency guarantees. Managing these membership changes safely is one of the more complex aspects of any consensus algorithm, and Raft addresses it with an elegant and robust approach known as joint consensus. The challenge of changing membership. At first glance, changing a cluster's membership might seem straightforward. Just tell the servers to vote with the new set of members. However, this naive approach can lead to severe consistency violations. Consider a 5-node cluster, cold, S1, S2, S3, S4, S5, from which you want to remove S5 and add S6, CNU. S1, S2, S3, S4, S6. Problem 1. Split brain risk. If S1 successfully changes to CNU, but S2 is still operating under cold, a situation where 2 leaders could emerge is possible. One leader could be elected by a majority of cold nodes, e.g., S1, S2, S3, and another by a majority of CNU nodes, e.g., S1, S2, S6, leading to data divergence. Problem 2. Availability risk. What if, during a transition, neither the old configuration nor the new configuration can form a majority quorum? The cluster could become completely unavailable. The core challenge is that consensus must be maintained during the configuration change itself. The cluster must agree on the membership change, and this agreement must happen atomically and consistently across all nodes. Raft's joint consensus mechanism tackles this head-on. Joint consensus, Raft's elegant two-phase approach. Raft avoids the pitfalls of direct configuration changes by introducing a transitional phase called joint consensus. Instead of switching directly from the old configuration, cold, to the new configuration, CNU, Raft transitions through an intermediate configuration that involves both. This intermediate configuration is denoted as cold CNU. In the cold CNU configuration, log entries, all new log entries must be replicated to a majority of both cold and CNU. Decisions, any decision, whether to commit a log entry or to elect a leader, requires a majority of both cold and CNU. Why this guarantees safety during transition? The joint consensus configuration is designed to ensure that it's impossible for two leaders to be elected simultaneously. If a leader is elected under cold, and then a network partition occurs, the remaining nodes trying to elect a leader must satisfy a majority in cold, CNU, to make progress. Since cold and CNU always overlap, it's impossible for both a cold leader and a cold, CNU leader to coexist and get a majority without one of them seeing a higher term. The overlapping quorum ensures that any server that could form a majority in cold for electing a leader necessarily overlaps with a majority in CNU if it's operating in cold, CNU. Similarly, it's impossible for a CNU leader to come into existence while a cold, CNU leader is still active. This overlapping majority requirement means that once a server transitions to the cold, CNU state, it can only make progress if it can communicate with and get agreement from members of both the old and new groups. This forces all operational servers to acknowledge the transitional state before the final configuration is adopted. Live reconfiguration steps, a walkthrough. Let's walk through the process of adding a server to an existing cluster, e.g., from a 3-node cold to a 4-node CNU. Initial state, cluster is in configuration cold, S1, S2, S3, S1 is the leader. Client request, an administrator or application requests to add a new server, S4. This request is sent to the current leader, S1. Leader creates cold CNU entry, S1 receives the request. It does not immediately switch to the new configuration. Instead, it creates a special log entry representing the joint consensus configuration, cold S1, S2, S3, CNU, S1, S2, S3, S4. This entry is appended to S1's log. Replicate cold CNU entry. S1 broadcasts this new configuration entry to its followers, S2, S3, using the standard append entries RPC. If S4 is a new server being added, it initially acts as a non-voting member, receiving log entries but not participating in quorum decisions for the old configuration. As soon as it starts receiving log entries from the leader and catches up, it can participate in the joint consensus. Commit cold CNU entry. Once the cold CNU log entry is replicated to a majority of both cold and CNU, it is committed. At this point, all active servers in the cluster are aware of and will operate under the cold CNU rules. From this point forward, any log entry, including the next configuration change, must be replicated and committed to a majority in both the cold and CNU sets. Leader creates CNU entry. Now that the cluster has safely transitioned to operating under joint consensus rules, the leader S1 creates another special log entry. This new entry represents the final new configuration, CNU S1, S2, S3, S4. This entry is also appended to S1's log. Replicate CNU entry. S1 broadcasts this CNU entry to all members of the CNU configuration, S1, S2, S3, S4. Commit CNU entry. Once this CNU log entry is replicated to a majority of CNU servers, which, due to the preceding joint consensus phase, means it must also have been committed by a majority of cold, it is committed. At this point, the cluster has permanently transitioned to the new configuration, S1, S2, S3, S4. The old configuration, cold, is now officially abandoned. Removing a node follows a similar two-phase approach. From cold to cold, CNU, where CNU is the reduced set of servers, then to CNU. If a node is being removed, once the CNU configuration is committed, the removed node simply ceases to be a part of the quorum and can be safely shut down. What if the leader is removed or fails during reconfiguration? The process is resilient. If the leader fails mid-reconfiguration, a new leader will be elected. The election process will use the currently active configuration, either cold or cold CNU. Any server that wins the election will resume the reconfiguration process from where it left off, based on the last committed configuration entry in its log. Limitations and considerations. While remarkably robust, Raft's membership changes are not without considerations. Performance impact. During the joint consensus phase, every decision requires 2 majority votes. This inherently increases the latency for committing new log entries, as it effectively doubles the number of required acknowledgements. Complexity to implement. While simpler conceptually than some other methods, implementing the dual majority logic for joint consensus correctly still requires careful attention to detail. Failure during reconfiguration. Although Raft handles failures gracefully, a reconfiguration process that is paused due to repeated failures can be a source of operational headache. Tools often provide mechanisms to query the current configuration and recover from stalled transitions. Quorum size. The number of servers being added or removed affects the number of messages and the complexity of the quorum checks. Adding many servers at once might be more efficient as a single reconfiguration, but it can also make the transition phase more fragile if many new servers are slow to catch up. Raft's elegant approach to dynamic reconfigurations is a testament to its design for practical implementability. It allows operators to manage their distributed systems flexibly, adding or removing machines as needed, all while preserving the ironclad safety guarantees that make Raft so valuable. With a stable cluster and a clear understanding of its configuration, the next step is to understand how external clients interact with this highly consistent system and how the system manages its ever-growing log. 7. Interacting with Raft, clients, read operations, and snapshotting. So far, we've explored how Raft ensures internal consistency and reliability among its servers. But how do external applications and users actually interact with a Raft cluster? How do they perform reads and writes? And what happens when the continuously growing replicated log becomes too large to manage efficiently? This chapter delves into the practical aspects of client interaction and the crucial role of snapshotting in managing log growth. Client interaction model. Clients, whether they are applications, other services, or direct users, need to reliably communicate with a Raft cluster. Since Raft operates on a strong leader model, all clients initially attempt to direct their requests to the current leader. Finding the leader. A client typically starts with a known list of all server addresses in the Raft cluster. It can then try to send a request to any server. If the contacted server is not the leader, it will respond by redirecting the client to the current leader, often by returning an error or a special message containing the leader's address. Clients usually cache the known leader's address and retry other servers if their requests fail or the cached leader doesn't respond. This mechanism allows clients to discover the leader efficiently. Request processing. Once a client successfully connects to the leader, it sends its command. For write operations, the leader processes the request by appending the command as a new entry to its own log, replicating the log entry to followers using append entries RPCs, waiting for the entry to be replicated to a majority of servers, committing the entry, applying the committed entry to its local state machine, finally sending a response back to the client. Idempotency. It's good practice for client requests to be idempotent, meaning they can be safely retried multiple times without causing unintended side effects. If a client sends a request to the leader, and the leader processes it but crashes before sending a response back to the client might retry the request. If the operation is not idempotent, This could lead to the same command being executed twice, e.g., deducting money twice. Raft implementations often include mechanisms, like client request IDs, to ensure uniqueness and prevent duplicate application of commands, thus making non-idempotent operations safe to retry. Handling leader changes. If the leader crashes or becomes unreachable while processing a client's request, the client's request will eventually time out. The client then needs to rediscover the new leader and resend its request. Since Raft guarantees that all committed entries are eventually applied by all servers, the client can be sure that once a request is successfully acknowledged, it's durably stored. Read operations, ensuring freshness, while write operations, which modify the state, inherently go through the leader and leverage the log replication process. Read operations, which only query the state, require special consideration to ensure consistency and freshness, especially for strong consistency. Read-only versus write operations. Reads don't usually generate new log entries, so they don't necessarily need to be replicated via the log. Simple reads can often be served directly by any server. However, this raises questions about how fresh the data is. If a follower serves a read, that follower's state might be slightly behind the leader's if it hasn't yet applied the latest committed entries. Linearizable reads. Many applications require linearizable reads. This means that once a write operation has completed and is visible to one client, all subsequent read operations, from any client, must also see the effects of that write, and reads must reflect the global, real-time order of operations. This is the strongest form of consistency. Raft provides techniques to ensure linearizable reads, leader-only reads, basic. The simplest approach is to always direct read requests to the leader. This guarantees you're reading the most up-to-date log. However, there's a subtle catch. A leader might think it's still the leader, but it could have been partitioned from the majority and a new leader might have been elected. If this happens, the old leader might serve stale data. Read index. To ensure linearizable reads from the leader, Raft implementations often use the read index technique. Here's how it works. The leader records its current commit index, the index of the last committed entry. It sends a heartbeat append entries RPC to a majority of servers and waits for a response. This confirms its leadership for the current term and ensures it hasn't been superseded. Once confirmed, the leader waits until its state machine has applied all log entries up to its recorded commit index. Only then does it perform the read operation and return the result to the client. This guarantees that the read reflects the state up to the point of confirmed leadership, preventing stale reads. Lease-based reads, leader lease. This is an optimization for read-heavy workloads. The leader requests a lease from a majority of followers. This lease is a time period during which the leader is guaranteed to be the legitimate leader, assuming its clock is synchronized with the followers and that no other leader will be elected. During the lease period, the leader can serve read requests directly from its local state machine without the extra round trip to a majority for each read, significantly improving performance. If the lease expires or is likely to expire, the leader renews it. Snapshotting, taming the ever-growing log. The replicated log is designed to grow indefinitely. Over time, it can accumulate a vast number of entries, which presents two main problems. Storage, the log can consume an excessive amount of disk space. Recovery time, when a new server joins the cluster or a crashed server recovers, it needs to catch up its log from the leader. Replicating millions or billions of past log entries can take a very long time, delaying its ability to participate in the cluster. The solution: snapshotting the state machine. Raft uses snapshotting to combat log bloat. Instead of retaining the entire history of operations in the log, servers periodically take a snapshot of their current state machine. This snapshot is essentially a point-in-time image of the system's state, similar to a compressed archive of all the commands applied up to that point. Once a snapshot is taken and safely stored, all log entries preceding the snapshot can be safely discarded. The snapshot effectively compacts the part of the log that has already been applied. A snapshot typically contains last included index, the index of the last log entry included in the snapshot. Last included term, the term of the last log entry included. State machine data, the byte stream or serialized representation of the state machine's state up to last included index. Installing snapshots. When a new server joins the cluster, or a recovering server is significantly behind the leader, e.g., its next index for that follower is less than the leader's last included index in its snapshot. The leader can send a snapshot to that follower using the install snapshot RPC. This avoids having to send potentially millions of log entries. The install snapshot RPC works by leader sends chunks. The leader breaks the snapshot data into several install snapshot RPC chunks and sends them to the lagging follower. Follower receives and validates. The follower receives the snapshot chunks, writes them to a temporary file, and validates their integrity. Follower loads snapshot. Once the entire snapshot is received, the follower loads it into its local state machine. This effectively brings its state up to the last included index of the snapshot. Discard old log. The follower discards any log entries up to the last included index in the snapshot, keeping only subsequent entries. This mechanism allows new or recovering servers to quickly catch up with the cluster's state, minimizing downtime and disk usage. Together, robust client interaction models, strong read consistency techniques, and efficient log management through snapshotting make Raft a complete and powerful solution for building reliable distributed systems. These theoretical underpinnings are validated by real-world applications, which we'll explore in the next chapter. 8. Raft in the wild, real-world applications and implementations. The true testament to an algorithm's value lies in its practical application. Raft, initially designed for understandability, has transcended its academic origins to become a foundational component in numerous widely adopted distributed systems. Its clarity has indeed translated into widespread and successful implementations. In this chapter, we'll examine prominent examples of Raft in action and discuss the operational realities of running Raft clusters. Case study. Etcetera, the backbone of Kubernetes. Perhaps the most famous and impactful deployment of Raft is within Etcetera. Developed by CoreOS, now part of Red Hat, and a cloud-native computing foundation project. Etcetera is a distributed, consistent key-value store that serves as the primary data store and configuration backbone for the hugely popular container orchestration platform, Kubernetes. Role in Kubernetes. Kubernetes, at its core, is a complex distributed system managing swarms of containers. All cluster configuration data information about pods, deployments, services, network policies, and the desired state of the cluster is stored and retrieved from Etcetera. Furthermore, Etcetera is used by Kubernetes components for crucial tasks like leader election among its control plane services, e.g., ensuring only one kube controller manager is active. How Etcetera uses Raft. Consistency and durability. Etcetera leverages Raft to ensure that all data stored within it is highly available, consistent, and durable across all nodes in the Etcetera cluster. Every write operation, e.g., updating a pod's status, goes through the Etcetera leader, which then replicates the change using Raft's log replication mechanism to a majority of its peers. Once committed by Raft, the data is guaranteed to be safe from single-node failures. Leader election. The Etcetera cluster itself uses Raft's leader election to determine which Etcetera instance is the primary node responsible for processing client requests and coordinating replication. If the current leader fails, Raft automatically elects a new one, ensuring minimal disruption to Kubernetes operations. Membership management. Adding or removing Etcetera nodes from a cluster utilizes Raft's dynamic configuration, change capabilities, joint consensus, allowing for maintenance and scaling operations without downtime. Operational considerations unique to Etcetera's Raft. The performance and stability of a Kubernetes cluster are directly tied to that of its Etcetera backend. This makes Etcetera an excellent case study for operationalizing Raft. Odd number of nodes. Etcetera clusters are almost always deployed with an odd number of members, e.g., 3, 5, or 7. This simplifies quorum debates and maximizes fault tolerance for a given number of machines. A 3-node cluster can tolerate 1 failure. A 5-node cluster can tolerate 2. Network latency. Etcetera's performance is highly sensitive to network latency between its members. High latency can cause slow writes, increased election timeouts, and leader flapping, all of which directly impact Kubernetes responsiveness. It's crucial for Etcetera nodes to be placed in low-latency environments. Disk performance. Etcetera is write-heavy, constantly persisting its Raft log and state machine to disk. Fast, low-latency storage, like SSDs or NVMe drives, is paramount to avoid I/O bottlenecks that can lead to delayed heartbeats and potential leader elections. Resource allocation. Dedicated CPU, memory, and network resources are recommended for Etcetera nodes to ensure predictable performance. Case study: Console service discovery and configuration. Another prominent example is Console, a multi-purpose service mesh solution developed by HashiCorp. Console provides service discovery, configuration, and segmentation functionality for distributed applications. How Console leverages Raft, service catalog, and health checks. Console's core function is to maintain a catalog of all services, their instances, and their health status. This critical information needs to be highly available and consistent. Raft is used to reliably store and replicate this service catalog information across the Console servers. Key value store. Similar to Etcetera, Console also offers a robust key value store for storing dynamic configuration data. This KV store leverages Raft for its strong consistency guarantees. Leader election. Console servers also form a Raft cluster to elect a leader among themselves, which handles all write operations and coordinates replication. While both Etcetera and Console use Raft, their client APIs and specific use cases differ. Etcetera focuses purely on KV storage for critical system components. Console offers broader service mesh features. However, their reliance on Raft for fundamental consistency and availability is a shared testament to the algorithm's versatility. Other notable projects and implementations. Raft's reach extends far beyond Etcetera and Console. Redis Enterprise. The commercial version of Redis uses Raft to ensure high availability and automatic failover for its sharded Redis databases. If a primary Redis instance fails, Raft helps elect a new primary among its replicas. TKV, a distributed transactional key-value database built as a cloud-native database. TKV uses Raft for replicating data across its regions, ensuring strong consistency for transactional workloads. CockroachDB. While not a pure Raft implementation, CockroachDB, a distributed SQL database, uses a Raft-like consensus protocol, specifically a multi-Raft variant, to replicate and distribute data across its clusters. Each range of data within CockroachDB operates as an independent Raft group. Drone, a CI/CD platform that uses Raft for leader election and state management in its server component. These diverse applications demonstrate Raft's flexibility. It's not limited to just key-value stores. It can be used to achieve consensus for any state that needs to be consistently replicated and highly available. Operational considerations for Raft clusters. Running a Raft-based system in production involves several critical operational practices, regardless of the specific application. Monitoring is key. Proactive monitoring of Raft-specific metrics is essential. This includes leader status. Which node is the current leader? Is it stable? Replication lag. How far behind are followers from the leader's log? High lag indicates issues. Applied index. How quickly are committed entries being applied to state machines? Election timeouts. Are elections happening too frequently? Network latency and throughput. Between Raft peers, these are critical health indicators. Disk I/O, latency, and throughput, especially for writes to the Raft log. Troubleshooting common issues. Leader flapping. Frequent leader changes can indicate network instability, overloaded leader, or misconfigured election timeouts. Split brain. While Raft prevents split brain, where two leaders commit data for the same term, network partitions can lead to a minority partition unable to make progress. Understanding logs and network topology is key to diagnosing. Slow replication, unresponsive followers often points to network issues, disk I/O problems, or resource starvation on the followers. Backup and recovery. Regular snapshotting and external backups of the Raft log and state machine are crucial for disaster recovery scenarios, e.g., losing a majority of nodes simultaneously, which Raft cannot recover from autonomously. Network configuration. Raft communication is highly sensitive to network latency and packet loss. Dedicated network interfaces, proper firewall rules, and avoiding network congestion between Raft peers are vital. Quorum management. Always deploy an odd number of nodes. Understand what happens if you lose a node, e.g., if you have 3 nodes and lose 2, you lost quorum and cannot make progress until one of the lost nodes recovers. Clock synchronization. While Raft doesn't strictly depend on perfectly synchronized clocks for correctness, minor clock drifts can affect election timeouts and troubleshooting. NTP, Network Time Protocol, or similar services are recommended. By understanding these practical aspects, organizations can effectively deploy and manage Raft-based systems, leveraging the algorithm's inherent robustness to build distributed applications that are not only theoretically sound, but also reliably perform in the demanding real world. However, like any algorithm, Raft constantly evolves, and optimizations and variants continue to emerge, the subject of our penultimate chapter. 9. Beyond basic Raft. Optimizations and variants. While the core Raft algorithm provides a solid foundation for distributed consensus, real-world deployments often encounter specific challenges that benefit from enhancements and optimizations. These improvements address performance, robustness, or specialized use cases, building upon Raft's fundamental safety guarantees without compromising them. Optimizations for performance and robustness. Several well-known optimizations have emerged to refine Raft's behavior. Pre-vote. The problem? In a partitioned network, a follower in an isolated minority partition might experience an election timeout. If it then attempts to become a candidate, it increments its term and sends request vote RPCs. When these RPCs reach the majority partition, which still has a healthy leader, the leader sees a higher term and steps down, disrupting the cluster. This is an unnecessary disruption if the isolated candidate can't actually win. The solution? The pre-vote optimization, proposed by the Etcetera team, introduces a pre-vote phase. Before incrementing its term and becoming a full candidate, a server first sends pre-vote RPCs to other servers. It asks if a majority would grant it a vote if it were to become a candidate, i.e., if its log is up to date enough using the election restriction rules. Only if it receives a majority of pre-votes does it then increment its term and proceed with a real election. Benefit? This prevents isolated minority partitions from causing unnecessary leader disruptions in the healthy majority, making the cluster more robust to temporary network instabilities. Read index and lease-based reads, revisited for implementation choices. As discussed in Chapter 7, ensuring linearizable reads without processing every read through the Raft log is crucial for performance. These techniques move beyond merely ensuring leader-only reads. Read index. This method trades a small amount of latency for strong consistency. The leader records its current commit index, then sends a heartbeat to a majority to confirm its leadership. Once confirmed, it waits for its local state machine to apply up to that commit index before serving the read. This ensures the read reflects all committed data up to the moment its leadership was confirmed. It provides strong consistency without needing to commit a log entry for the read itself. Lease-based reads, leader lease. This highly performant optimization relies on synchronized clocks within the cluster, e.g., using NTP. The leader periodically obtains a lease from a majority of followers for a short, fixed duration, e.g., 100 ms. During this lease, the leader can serve read requests directly from its local state machine without contacting any followers. It assumes that no other leader can be elected within that lease period, because any election attempt would take longer than the lease duration. If the lease is about to expire, the leader renews it. This significantly reduces read latency, but introduces a dependency on loosely synchronized clocks and assumes network delays are within predictable bounds. Leader transfers. The problem. Sometimes you need to change leaders gracefully, perhaps for maintenance, load balancing, or to move leadership to a server with better network connectivity. Forcefully killing the leader triggers an election, which is disruptive. The solution: leader transfer allows the current leader to voluntarily step down and hand over leadership to a designated follower. The process involves the current leader ensuring the chosen follower's log is completely up to date, refusing new client requests, sending a special append entries RPC or a request vote RPC to the target follower, making it time out and initiate an election, granting its vote to the target follower. Benefit: provides a controlled way to manage leader changes, reducing downtime and impact on client operations. Non-voting members. The problem: for very large clusters or specific disaster recovery setups, you might want servers that receive log entries but don't participate in quorum decisions. This could be for archival purposes or to increase the number of read replicas without increasing the cost of writes, as more voting members mean more nodes to update for a majority. The solution: Raft permits non-voting members. These servers are treated as basic followers for log replication, but are excluded from the calculations for achieving a majority in elections or commitments. They are typically added via a dynamic configuration change that designates them as non-voters. Benefit: allows for flexible deployment topologies, such as having a larger number of read-only servers or geographically distant archival nodes that don't increase the quorum size for regular operations. Raft vs. other approaches revisited. While Raft is excellent for many use cases, it's not a silver bullet. Understanding its strengths and weaknesses relative to other distributed system paradigms is important. Paxos. Still theoretically powerful, but practically complex. Raft often suffices where Paxos might be considered overkill. Unless you're designing a system for a specific, highly academic environment demanding features or proofs unique to Paxos, Raft is almost always the preferred choice due to its understandability. Primary backup models. Simpler than Raft, often with a single designated primary that replicates to a backup. Good for simple failover, but typically lack automatic, robust recovery from multiple or complex failures. Raft provides a more sophisticated, self-healing mechanism. Consistency versus availability, CAP theorem. Raft is a CP, consistency and partition tolerance system. In the event of a network partition, Raft will prioritize consistency. The partitioned minority will become unavailable, unable to elect a leader or commit new data until the partition heals. This is a fundamental trade-off. For systems where availability is paramount even in the face of partitions, and eventual consistency is acceptable, like some NoSQL databases such as Cassandra, an AP, availability and partition tolerance, model might be more suitable. However, for applications requiring strict data integrity, like financial transactions or configuration databases, CP systems like Raft are indispensable. Industry evolution. The field of distributed systems is constantly evolving. As new demands emerge, e.g., global consistency across geographically dispersed data centers with high latency, edge computing, consensus algorithms are adapting. Extensions to Raft, such as multi-Raft, running multiple independent Raft instances, each managing a subset of data, are common in distributed databases to handle massive datasets. Research continues into faster consensus algorithms, fast Paxos, optimistic Paxos, and new distributed transaction models. However, the principles introduced by Raft remain highly relevant. These optimizations and conceptual differentiations illustrate that Raft, far from being a static algorithm, is a living, adapting framework. Its core strength lies in its modularity and robust foundation, which allows for these practical enhancements to meet the evolving demands of distributed computing. This constant evolution is a stark reminder that while the basics are crucial, the future of reliable distributed systems holds even more fascinating challenges. 10. The future of reliable distributed systems. We've journeyed through the intricacies of the Raft consensus algorithm, from its philosophical underpinnings to its concrete implementation details and real-world applications. We've seen how Raft orchestrates order in chaotic distributed environments, transforming unreliable components into a cohesive, highly available, and strongly consistent system. As we conclude this expedition, it's essential to cast our gaze forward. acknowledging Raft's limitations, exploring emerging challenges, and understanding its enduring legacy in the ever-evolving landscape of distributed computing. Limitations of Raft. While Raft shines in many scenarios, it's crucial to understand where its design goals introduce inherent limitations. Single leader bottleneck. Raft's strong leader model, while simplifying understandability and consistency, can become a bottleneck for extremely high-throughput write operations. All writes must pass through the leader, which then replicates them. This can limit the system's overall write scalability. For systems requiring truly massive write throughput that cannot be sharded, broken into smaller, independent Raft groups, alternative architectures or consensus algorithms might be considered. Geographic distribution challenges. Raft is best suited for clusters where network latency between nodes is relatively low and reliable. Deploying a single Raft cluster across widely dispersed data centers, e.g., continents apart, introduces significant network latency, which directly impacts the performance of log replication and commitments. This can lead to slower operations and increased election timeouts. While solutions like multi-Raft, where smaller Raft groups are formed within regions, can help, achieving true global consistency across a single, monolithic Raft instance becomes impractical. Complexity of very large clusters. While Raft technically supports a large number of nodes, managing and operating a Raft cluster with hundreds or thousands of members can become an operational burden. The overhead of heartbeats, append entries RPCS, and reconfigurations increases with scale. This is why partitioning data into smaller, independent Raft groups, often called sharding or multi-Raft, is a common strategy for very large distributed databases and systems. Emerging challenges in distributed systems. The world is not standing still, and new computing paradigms are constantly pushing the boundaries of what distributed systems must achieve. Serverless architectures. In a serverless world, where functions are ephemeral and triggered on demand, the traditional notion of a long-lived, stable Raft cluster might not fit directly. However, the underlying need for shared state and consistent coordination across these transient functions still exists, perhaps leading to new consensus models or ways serverless platforms integrate with foundational consensus services. Edge computing. As more processing moves closer to data sources, e.g., IoT devices, smart cities, the challenges of highly intermittent connectivity, extreme latency variability, and resource-constrained environments will demand lighter weight, more resilient, and perhaps localized consensus mechanisms. Highly consistent global databases. The ultimate dream is a single, globally distributed database that offers strong consistency and high availability with low latency, anywhere in the world. This is a monumental challenge that existing consensus algorithms struggle with individually. New research in areas like geographically partitioned consensus, distributed transactions, and sophisticated replication strategies continues to push this frontier. Beyond crash failures. While Raft assumes fail-stop behavior, a server either works correctly or stops. Byzantine fault tolerance, dealing with malicious or arbitrarily misbehaving nodes, remains a niche but important area, particularly for blockchain and highly trust-sensitive environments. Raft is not designed to handle Byzantine faults. Related and complementary concepts. Raft doesn't exist in a vacuum. It often works in conjunction with or is complemented by other distributed systems concepts. Distributed transactions. For operations that span multiple independent databases or services, distributed transactions, e.g., two-phase commit, sagas, are often used to ensure atomicity. Raft ensures strong consistency within its own replica group, but for operations across different Raft groups or other data stores, higher-level transaction protocols are necessary. Eventual consistency. While this book has focused on strong consistency with Raft, it's important to remember that huge-scale systems often use eventual consistency for performance and availability gains. This model allows data to temporarily be inconsistent across replicas, eventually converging to the same state. Raft sits at the opposite end of the consistency spectrum, designed for where strong guarantees are non-negotiable. Microservices and service mesh. In a microservices architecture, services communicate over a network. A service mesh, like Istio or Linkerd, helps manage this communication, providing features like load balancing, circuit breaking, and traffic routing. While Raft isn't directly part of the service mesh data plane, the service mesh's control plane might use consensus algorithms to store and manage its configuration consistently. The ongoing quest for reliability. The digital world runs on distributed systems, and the demand for reliability will only grow. Understanding foundational algorithms like Raft is not just an academic exercise. It's a practical necessity for anyone building or operating modern software infrastructure. Raft demystified the previously obscure realm of distributed consensus, making its principles accessible to a broader audience of engineers. Its design for understandability has profoundly impacted the industry, accelerating the adoption of strongly consistent distributed services. The quest for reliability is an ongoing journey. As systems become larger, more globally dispersed, and more dynamic, consensus algorithms will continue to evolve. But the core problems, agreement in the face of failure, ensuring consistency, and providing fault tolerance will remain. Raft has provided a clear, effective solution to these problems for a significant class of distributed systems, and its principles will continue to inform and inspire future innovations. We encourage you to continue your exploration of this fascinating field. The resources below offer avenues for deeper dives into Raft and the broader world of distributed systems. May your systems be reliable and your logs always consistent. Further reading and resources. Original Raft paper, In Search of an Understandable Consensus Algorithm by Diego Ongaro and John Ousterhout, 2014. Available on raft.github.io. The Raft website, raft.github.io, contains animations, formal specifications, and links to various implementations, etc. documentation. For a deep dive into an applied Raft system. Console documentation, another excellent example of Raft in practice within a broader system. Designing Data-Intensive Applications by Martin Kleppmann, an excellent book covering a wide range of distributed systems concepts, including consensus. Distributed Systems, Concepts and Design by G. Coularis, J. Dollimore, T. Keinberg, G. Blair. A comprehensive academic textbook on distributed systems. Academic papers and conferences. Look for papers from PODC, Principles of Distributed Computing, OSDI, Operating Systems Design and Implementation, SOSB, Symposium on Operating Systems Principles, for cutting-edge research in distributed systems.